About an hour ago, here in the physics department of Quaid-i-Azam University, we had a fantastic lecture by Bruce Damer, who's here with me. Bruce is a person of extraordinary abilities. He is, on the one hand, a designer of spacecraft. He's got various ideas that have actually caught on. And NASA has often approached him, asking him, how would you design this or that? But most recently, he's been working on the origin of life, something that has enthralled people, something that everybody wants to know the answer to. So Bruce, it is a pleasure to have you over here. Can you, in 2 minutes, tell us what you talked about this afternoon?
Yeah, I think basically it comes down to Charles Darwin, the sort of father of evolutionary theory, who thought, and he wrote in a letter in 1871, that life could have started in a warm little pond somewhere with all the right chemicals, and that those chemicals would somehow grow in number and in length, and that this would be the way life can start. And in our work is to return to Darwin's warm little pond and realize that it's more than a warm little pond. It's a hotter pond, kind of like a bathtub with hot water coming into it, into which things almost like soap bubbles can form and encapsulate those, what are called polymers, those special chemicals. And each soap bubble is moving through the water, and it either pops or it does not. And the surviving soap bubbles carry the little polymers that help them survive down for a new cycle. So if you cycle your bathtub soap or your warm little pond or hot little cycling pond, the bubbles get a little smarter and more capable through time, and gradually booting up, like a computer, the operating system of life.
Well, you understand that a lot of people here and a lot of people in your own country don't like Mr. Darwin very much. And yet you're convinced that life evolved from a chemical soup. Why are you so utterly convinced about that?
Well, it's an interesting problem. So it fascinates a nerd mind like mine. So, for example, you could take the easy way out and say that, a creative hand made it. But then you have to ask the question, what made the creator that made life? And you can't actually work on the problem if you say, well, it was just created by, say, a lightning bolt or a turtle or a god. You can't then work on the problem because you've closed the door. And so for an inquiring mind that studies how life actually works, how things grow from the ground, how things evolve, which clearly they do, it's much more interesting to actually ask the question, well, how can it all start?
So from these very simple atoms, hydrogen, oxygen, carbon, nitrogen, and so forth, how do we make the path up towards bigger, more complex molecules? And how much do we understand of this? I do recall you're telling us this afternoon about that famous experiment due to Urey and Miller, in which you have atmospheric sparking and you get these simple atoms making amino acids. But how much beyond that have we understood?
We've just barely now begun to understand how that system can work. So with Miller and Urey, they sparked a gas that had certain building blocks that they thought would be kind of like the early atmosphere. And in the bottom of the flask where this sort of black-brown matter was made, and that was amino acids, part of the building blocks of our bodies. But in order to get more than just a building block, in order to get the beginnings of the first little cell, the first simplest cell, you have to put more things in your mixture. So you have to put the building blocks of the membranes of the cell, the bubbles, if you will. Then you have to put other little molecules that talk to each other in some functional way. And we've only just learned how to do this in our field in the last 10 years, how to create those things called protocells and put special polymers, special molecules in them, or randomly generate them through this wet-dry cycling. And so this is a new path in science. It's a new discovery.
So when would you say that a bunch of atoms have gotten together in a sufficiently organized way to be able to call life? Where would be that criterion that separates inanimate matter from matter that is living?
That's the question of the age. In a sense, it was the question asked by alchemists for 500 years in Europe, for example. Their mission was given to them by various kings. It was the first funders of their work, was not necessarily to turn lead into gold, but to actually animate non-living matter, dead matter, into living matter. That was the alchemists' objective, really. It was their highest order thing. And of course, this is a really difficult problem. But since we've discovered the power of computers to boot up more complex phenomena, one of them being the internet. The internet was built not by an individual computer, but by a lot of computers running simple services that talk to each other. And it's built this enormous thing called cyberspace, or the internet. And that's a teaching tool for us as we look now at chemistries that can cycle and create more complex compounds that seem to work in networks. So we literally take the technology of the internet and computers and map it onto chemistry, and we can find pathways for chemistry to create more complex things, that some of which might be lifelike properties, like a simple genetic code or a simple metabolic cycle is observed in such a thing. It may never become life. We may never be able to create life in the lab that way, but we can get a suggestive pathway toward a living world that might be what scientists call a plausible explanation.
So you could say that the internet is about distributed intelligence. It doesn't have to be concentrated in one particular place. It doesn't have to be in one mind. It can be shared between different minds, between different computers. Mm-hmm. But that is not by itself capable of replication, or is it?
Well, in a way it does, because the internet is mostly driven by people who sit and make sure servers are operating, does a form of replication. For example, software releases that come and update. There's constant updates flowing throughout. Different code is arriving and it's upgrading servers. Servers are under attack by viruses that are made by people, and that creates almost like an evolutionary competition. And in pure systems where there's no people creating viruses, you can design virus systems digitally that will evolve code and responses. So we can actually build what they're called artificial life systems to create a simulacrum of biology and this idea of booting up chemistry. That's a field I worked in for about 5-6 years or so.
Mm-hmm. One of the themes of your talk was that competition and cooperation both exist, and that in fact it is cooperation that allows cooperation between molecules, in fact, mm-hmm. that allows the building of more complicated molecules that ultimately arrive at the prokaryote, going on to the eukaryote, going on to higher forms of life and so forth. On the other hand, there is also the competition between organisms, and they have to compete for food, they have to compete for space, other requirements. How do you see that working out philosophically in human society?
Well, what's interesting is if you look at a modern organism, say like a lion and a gazelle in the plains of Africa, very high-tech system. So the lion is hunting the gazelles can outrun it or not outrun it. The lion may be eating a certain number of them, the young ones and the old ones and the sick ones, but it actually is a cooperative system because the gazelles that are remaining are the strongest. So genetically, they advance. They can run faster, etc., etc. The lions advance with their capabilities. The same thing happens in the microbial world, but it's a little different. The microbial world, for 80% of the time life was on Earth, microbes pretty much were existing as a consortium, as a network. So the top layer of microbes was capturing sunlight, generating chemical feeding for the next layer. There may have been a black layer further down where things are degrading and being recycled. So it's called the consortium model. And if you took a piece of that, and nothing's moving there. There's nothing technically eating another thing because these are simple bacteria. They're competing for resources, but it's the overall colony, it's the health of the colony that matters. And some organisms will reduce their metabolic activity to increase the viability of the colony. So that's the consortium model of life, and that's the dominant model for life on Earth.
Does this contradict the notion of a selfish gene?
It, in a sense, confounds and confuses the notion, because now we know about epigenetics, we know about horizontal gene transfer, we know about how systems, well, going back to the original, I think the original assumption was made in the 19th century because biologists would take a cell or an organism away from its environment and study it on a slide, dead or alive. They would study individuals in isolation. And in the 20th century, that was rectified when we realized you can't do that because you can't understand behavior in isolation. Mm-hmm. Even for an organism complex like ourselves, you can't understand behavior of a bacterium apart from its environment. So, in a sense, it isn't about a single selfish gene, it's about huge complexes of genetic material that are in constant exchange. It's a big operating system. It's not an individual program. So programs and computers don't exist in isolation from their environment either. So I think we had to broaden our thinking a little bit.
But a computer program is very deterministic. If you start it in one initial state, it will always end up in one final state. Now, if a gene is actually composed of atoms, then responding to one environment, it will always have exactly the same response. Mm-hmm. But of course, the environments are different. That's what you're saying. And so therefore, you would see the gene responding in different ways to that. However, as Dawkins emphasizes, he says that ultimately the gene has a single purpose, which is to maximize its spread. Mm-hmm. Now, in your way of thinking, is this something that actually conflicts with the idea of cooperation between species?
Yes,
within species?
I would say yes and no. Locally, that gene, basically that the cell needs the resources to divide. So there's a driving force for a protocell or a cell to make a division to pass its heritable traits on, its genes on. But it can't do that division without the context of the support of the community in which it exists. So, for example, if food supplies ran out around Islamabad, mm-hmm. we wouldn't be able to reproduce. We would suddenly have a sudden crash of numbers of people, relatively quickly because we don't understand how to make our own food. We can't grow our own food. So we're totally dependent, even though we're in competition with everybody on the GT road and everybody is kind of in competition, but we can't exist without the truck driver and without that farmer. We could exist without certain politicians, but without the guy making the paradas and, politicians.
On the other hand, if you're on our roads, you see the competition outweigh the cooperation.
Right. Although I've noticed on Pakistani drivers, this is an amazing phenomenon. So you're driving in Pakistan, which I would never do. I'd be too terrified. But if there's the smallest space, there's a motorbike coming up, right? And everybody has like a sixth sense, like ESP, that they know no one collides with anybody that I've seen so far.
The motorcyclists are very calculated.
But I don't want to tell you about what happened to me last week.
But what's fascinating is that the traffic is somehow optimizing itself here in ways that you don't see in California. So, for example, the crazy people who are trying to make the right turns across the motorway, right? I tell you, there's like 300 cars get through that. Whereas in California, maybe 6 cars would get through that before people would get confused. Maybe 300 cars and 100 motorcycles will get through that turn. And it's somehow way more optimized because I think people are more aware of what's going on. And they actually are polite sometimes. You may not think so, but there's like some kind of hidden rule by which if somebody is coming and cutting in front of you, there's a point at which you actually let them come in. Whereas in the United States, people are like, I'm going to block them, right? I'm going to block them for my own selfish purposes, and it actually slows the traffic more. In Germany, they'd be simply just shocked that somebody was doing this, but not following the rules. But in Pakistan, there's this incredible optimal algorithm going on of politeness, craziness, and using things that aren't roads as roads. And so more traffic actually flows than perhaps in California.
Bruce, you also spoke about the possibility of life on other planets and what it might take to have life over there. How do you think your hot springs model adapts to Mars or perhaps some exoplanet?
It actually gives us, for the first time, a framework. So, for example, the search for life on Mars, NASA was always wondering, do we go to a delta? Which was clearly there was water flowing into a crater. Do we go to a plain? Do we go to an ice cap? Where do we go? What do we do? And without a model for where life can begin, there's no way to know. There's no way to find to find any kind of fossil evidence or organics or something. Now, with this hot spring model, which not only could have been the place life starts, but hot springs on Earth always have incredible life in them. They have the most powerful ability to preserve evidence for life. So those three properties means, you go to hot spring locations on Mars. And there's one that was discovered by the Spirit rover around 2006, and when it ended its mission, discovered an old Yellowstone preserved, no water going through it. But from orbit, they've discovered 3 or 4 more hydrothermal locations on Mars, because Mars had oceans, it had an active climate, and it had volcanism. Mm-hmm. So they've actually said, there's several locations where there's clear hydrothermal activity. So it's wonderful because it whittles down the sites. Mm-hmm. It's actually the only thing we have to go on, really, at this point.
Well, this afternoon we had something like 150, 160 people in the audience, but now around this table we could accommodate only 20 or so. They have a lot of questions to ask, and we had all sorts of people belonging to different disciplines and coming from different places. Some came from Lahore, a lot of people are here from Islamabad, and there's some old people and there's some young people. I noticed 2 very young people at that end of the table, and they're itching to ask questions.
I have a question to ask about your other TED Talk about Shepherd. For the asteroid to slow down and for you to extract the materials you need other materials to do that. So when those materials finish, where do you get them from? Do you go back to Earth and collect them again, and then you move on, or you get them from some other place?
What's your name?
Sasha,
that's a very good question. So what we have to do...
But tell us first what she's talking about your...
So this is an idea that I came up with Peter Janiskins of the SETI Institute, who's a meteor astronomer. He studies meteorites and things that come in from space. And then Julian Knott, who's a balloon designer. He designs the balloons that people jump from. The Red Bull guy who jumped, that's Julian's balloon. So we came up with this is the idea of extending a balloon around an asteroid. And then what we have to do is we bring our own gases to it. So we bring a gas called xenon, and we put in just 1/10 of the atmosphere of the Earth. So if this is 10, we put in 1 unit. It's a very light amount of gas into the enclosure, and we're not touching the asteroid because they tend to be rotating, and it might be 1,000 tons. But when we just introduced a little wisp of this xenon gas, it causes friction with the asteroid and will slow it down. And just to potentially a few days stop it with friction in the gas inside this balloon. And then we use the waves of gas like a sailing ship, to put force onto the asteroid, and it will rotate like a sailing ship does into the wind, and then it'll push it very gently. it'll push it very gently along and gradually move its orbit. And then we fire our gas supply out the back, and we can maybe move it to the orbit of Earth or Mars. Now, here's the answer to your question is, what happens when you run out of the gas that we're using for this? Well, there's gas in the asteroid, and it's coming from water, ice, and methane, and carbon dioxide. So what we then do is heat up the gas that's in the container using sunlight, because on the outside of the balloon, the sun's hitting it, heats it up, and then stuff starts to come off the asteroid. Little tendrils of water ice will melt and evaporate into the enclosure, and so suddenly we start having gases made of water vapor and CO2 and stuff. Now there's more gas than just the ones we brought, and then we use our pumps, and we pump that gas out, and it's full of dust. That's going to be a problem. It comes, and those gases come into tanks, and the tanks have hot and cold plates in them, and then they basically turn those gas into liquid, and then we have this great big tanker block full of water, which we crack into hydrogen and oxygen, and now we made a fuel. So by the time that we're in the orbit around Earth or Moon, we have this gas station, this petrol station full of stuff to be used, water and hydrogen, oxygen, and methane and things like that. And so spacecraft can come up and fill up. So if they're going to Mars, we can supply all of the fuel and water for crews to go to Mars. And then we can also park one of these things in Mars orbit full. So when the crews get there, they have fuel to return to Earth and to land all over Mars. Plenty of fuel. So that's the answer.
My name is Aslam Chauhan, previously from this department here. About epigenetics, I came across an article from Islamic University, and they said epigenetics is a fact, and if you have a personality, it will pass on to the next ones, which means that the family line of the prophet cannot make any mistakes. So it's a very interesting aspect of epigenetics. I don't know how much it is stretching. The other thing is this hot spring thing. It's quite possible life is existing under liquids, and they are quite intelligent and propagating, and they might never surface. So just an alternative idea about these things.
Like dragons under the ground?
No, I mean, like in some moons of Saturn, and you have liquids, and that could be existing there, because it's more difficult to exist outside. So maybe they have structure inside.
It could be that in these moons of Saturn, that there's microbial life in the oceans. What's interesting is we have perhaps intelligent life in our own oceans, cetaceans, dolphins, whales, that have very big brains, that they don't spend any time in airports or in space or traveling. They have languages, and they have a long evolutionary history, but they don't surface, as you pointed out. So they're not really visible to us, or maybe to detection.
My name is Najaha, and I'm an undergraduate student. My question is that in the rocks you showed, you said that it was the oldest evidence of life, around 3.5 billion years old.
Mm-hmm.
So are we aware of life existing before that, or is there no evidence of it and we know that there was life?
That's a very good question. Recently, in the last 2 years, there have been what have been putatively stromatolites found in Greenland rocks that have been dated at 3.7 billion years. And the colleague that we work with in Australia actually was the one called in to look at these rocks, and he declared it was a stromatolite. So perhaps we're now pushing to 3.7. There's evidence for chemical evidence, isotopic evidence, for the suggestion that there was life around 4 or even 4.1 billion years ago. But there's no surviving Earth's crust. There's no rocks to study from that period. So we can't get those wonderful textures that really tell a story of a whole community. We can only get little chemical hints here and there. and it's difficult beyond that. It's all been erased.
Well, earlier on, the Earth was liquid, and you just had a molten ball floating in space.
Well, the interesting thing is that after the collision that may have created the moon, you had a complete melting of the entire lithosphere again. So the Earth may have congealed earlier and had liquid oceans. Since Mars actually solidified and probably had its hydrosphere before Earth. So this collision that formed the moon, this is the current thinking, remelted everything. And so Earth had a reset. But it ended up with this nice huge moon, which was very handy. It helped keep our plate tectonics going. It helped protect us, because all the craters on the moon were impacts that could have come here. And in the period between about 4.1 and 3.8 billion years ago, the inner solar system was a shooting gallery. There were all these rocks everywhere, and there was all these impacts going on. And then Jupiter seems to have moved out and pulled all that rock debris out past Mars, and that's called the asteroid belt. If Jupiter hadn't gone out, there would have been dangerous conditions for probably another couple billion years with this material. And it's hard to imagine life having an easy time of it. So I don't know what the original question was, but...
Yeah, you answered my question.
Yeah. My name is Ibne, and I'm by profession an architect. The probability of life forming, as you have suggested and as previously others have suggested, what is the probability of that happening across the universe? What is the probability, or I should ask, what is could be the the number of populations of intelligent life form that is possible in the far out space?
Mm-hmm. I think the quick answer to the question is, if life can start in these cycling systems of water, air, and mineral interfaces where they're cycling and you can get a system going, I think that microbial life may be reasonably easy to start. In 1 trillion exoplanets, there may be a percentage that have microbial living systems. But there's a long way between a microbial start and complex life. And if we're now getting very humbled by this realization that the 3 billion years it took the microbial world to condition, to transform the planet, to give us free oxygen in the atmosphere, to control the temperature and the gas content, and to survive all these terrible events, and to have the right catastrophes at the right time. Because you not only, like for instance, Bob Hazen in his book, which is a wonderful book about the phases of geological history of the Earth, he said there's evidence at one point, I think between 2 and 3 billion years ago, that the plate tectonic system was stalling. Like Mars's crust is called a stagnant lid. It doesn't have these plates. It's just one great big frozen thing all the way down with hot plumes coming up for volcanoes. It's not a very good environment to cycle carbon and to keep a dynamic system going. Whereas we have these plates that dive down and bring organic materials down, and then they come up volcanoes, and we have this recycling system. But between 2 and 3 billion years ago, it stalled. And it only got restarted because there was a massive asteroid impact at one point that restarted the plate tectonic engine of the planet. So it's not only avoiding or surviving catastrophes, it's also the right catastrophe at the right time to bring you to complex life. So, and also planets die probably quite easily. If Mars could go out of the habitable zone and if Venus could go out of the habitable zone, you have in these exoplanet models the idea of orbits being unstable. Now, we're used to what we think in all exosolar systems orbits are stable. That's not the case. If there's an intruder that comes through, if one of the large planets goes into an unstable orbit, it will pull out everything, and suddenly planets are thrown into crazy orbits, and it kills the possibility. So space is hazardous. I mean, the universe is a very, very hazardous place. And to get to the absolute right conditions for 4 billion years, where we don't have an upset, we don't have a gamma ray burst event that's nearby that sterilizes our planet. or we don't go through a star nursery in our orbit around the galaxy, which also could sterilize the planet because of radiation. None of these things happened.
What you're saying will make people who believe in intelligent design very happy?
How so?
Oh, that it is so utterly fortuitous that we happen to be here, because you could have this and that and that, and it's got to be some absolute miracle, something designing.
Or it's all in the numbers. Because if we have a trillion, so you think about it, and this is what I was explaining earlier, that the probability of, say, one of the arguments for irreducible complexity is that, it's impossible to get a long polymer, like a long piece of RNA that's 200 units long, to just be, that does a certain job. And so it's argued that this could never have started. Well, this is usually people who don't do any work, right? They're not doing any thinking, and they're even in science, there are people who would make this claim. But if you actually work in the field and you know what you're talking about because you can observe it, we take a gram quantity of lipid, we take an even less quantity of RNA building blocks in a little vial like this, and within minutes we're making 1 trillion containers, 1 trillion protocells, and we're making billions or trillions of random sequences of RNA. And when we put them on our gels and we see this great big bands, there's the products right there. And there's trillions of them. And this is in a very, very small container. So you can imagine a pool or 1,000 pools on a volcanic landscape all exchanging information, exchanging fluids. It's a gigantic computational system for trying out possibility. And that computational system is still going on now. It's called the living world. It just basically is still doing those tricks of exchange, of trying into computational space. So the Earth, even if the Earth was 2/3 ocean and 1/3 land, it doesn't really matter because you're going to have volcanic landscapes. And back then, everything was hot springs. So the ocean formed coming out of the atmosphere. But for a period of time, the entire Earth was a hot spring. It was cycling hot fluids through the bottoms of the ocean, which generated the salinity for the oceans. So the oceans would have been, fresh water mostly, and it generated the salty oceans. It fed into the volcanic systems, and it was basically bubbling hot springs everywhere. The whole planet was that. And then the oceans gradually filled up. We luckily had enough inventory of water. Mars had really shallow oceans that were gone in 1 billion years. Ours are still here. We're very fortunate. Venus is, if it had oceans, they went into the atmosphere and created this basically hothouse hell for Venus. So it's almost like the old saying about Goldilocks. The porridge was just right. It wasn't too hot or too cold. So that's why astrobiologists use the term Goldilocks zone.
But you must tell our friend about the Drake formula.
The Drake equation is a wonderful thing. It's created by somebody who lives in our area named Frank Drake. And it's a formula which tries to estimate the intelligent civilization, say, in a galaxy. So it's the number of stars that are probably of a certain type, the number that have circular orbits, have rocky planets, have smaller planets, not just gas ones. And it goes from there. And then the ones that are likely to have life emerge on them. I wrote 4 new terms to the Drake equation for a presentation at the SETI Institute. Frank wasn't there, but Seth Shostak was there. Some of them were quite funny, but basically I wrote a new Drake equation extension, which was how many, like in Star Trek, to boldly go, right? How many civilizations take the effort or evolve to the point where they send starships out to say hello, come into orbit, say, hi, how are you doing? And it's quite small, even smaller, because you have to have an intelligent civilization that does science for a long period of time, science and technology, and survives, doesn't blow itself up. Then it has to also fund visionary nerds. Visionary nerds for a long period of time. And then the next part of the equation is visionary nerds that have no real benefit. They don't return on investment, because the investment's very large to do this kind of work, and it doesn't necessarily economically motivate anybody. And then the last term was whether these visionary nerds would be supported for millions of years. So probably the reason there aren't starships around is because civilizations like China, when China created those great fleets, the fleets that may have reached Europe, the fleets that went out, eventually the emperor burned the fleets, and that was the end of exploration.
Oh, but don't you know that there were spaceships going from Earth to Mars? That's what Narendra Modi tells us.
Who's Narendra Modi?
Oh, he's the Prime Minister of India.
Oh, okay. Well,
you include the Fermi's paradox in your.
Let's take one last question, and then because time is getting on.
My question is that instead of, it's about shepherd, that instead of colonizing another planet and spoiling like we are spoiling Earth, why don't we use shepherd, make a biosphere, and then live in that?
Yeah, that's an excellent question. There was a man in the 1970s named Gerard O'Neill. He was a physicist actually at Princeton. And his idea was to create these enormous spheres in which people could live on the inside, that we could create much more livable surface area than is available on the Earth using these kinds of constructions. And another person that I work with now and then is Freeman Dyson. And Freeman Dyson is a physicist at the Institute in Princeton, and same place really. And he said, if you want to look for an advanced civilization, look for a civilization that has built a sphere in space around its entire star. Its entire star. It's capturing pretty much all the energy, and it's created a huge, beautiful area to live in because they've made the sphere that the sun is inside, kind of like a gigantic version of Shepherd. And that if somehow you could detect that the radiation coming out of this star was somehow strange, it may be because it's in a Dyson sphere around the sun. So perhaps that's what advanced civilizations ultimately do is they create whole new biospheres. And I think we're going to have to, we will have no choice if we wreck this one. We better start, but when we create a new biosphere and learn how difficult it is and the very fine points in managing biospheres that might have only 1 million people in them, we're going to look back at the Earth and say, whoa, we're wrecking that biosphere. Are we crazy? Let's manage it better. We learned how to manage this one. We can learn how to take care of that one better.
And just to let people know, Freeman Dyson doesn't have a PhD.
Yeah.
And yet he's one of the most brilliant physicists of the last century. Did his great work in the 1950s, 60s, even in the 70s. Yeah. One last question before we end.
So, Deva, my question to you is that Stephen Hawking recently has been talking a lot about parallel universes there, and what he proposes is that there would be a Dr. Bruce Damer there sitting right now somewhere, and Dr. Ulfa, and maybe Hamad Masood as well. So, how does he get to make that claim? What's his reasoning behind that? And so, if you allow me, there's one question to you.
I think both questions are to him.
Okay, so it's not very, it's not related to the science that we're talking about, but it still relates to science and the way we perceive science. Now, religion and science, they do not go hand in hand. Myself, being a person who understands and knows that science is for real, and the moment, and spirituality is important as well. Now, I do not want to let go of my spirituality, and the only way I know of that is my religion. How do I get to live a life where when I get into a science room, I just do my science and do not let my other side meddle with that? And then how do I have a daughter who's 4 years old, so how do I actually get that into her head? Do I get to write a letter like Richard Dawkins did to her daughter, a famous letter? How do I do that? How do I balance both?
I can give you answers of 30 seconds each. Well, first of all, about parallel universes. It is perhaps a a requirement of quantum mechanics and perhaps not, because when we make a measurement, at the point of making a measurement, we cause the wave function to collapse. And this has been something that has troubled the founders of quantum mechanics. It is still a very troubling problem today. One escape from that is that each time you make a measurement, you create a new parallel universe. Now, personally, I think that this is perhaps something that is not testable, and therefore to me is not very interesting, because if there is a parallel universe, if there's a parallel you, and I can never talk to you or be able to communicate with you in any fashion, then this then falls outside of the ambit of science. And so there might be or might not be. I think the problems of quantum mechanics will be solved without actually inventing the notion of parallel universes. On the issue of the relation of science with religion, well, I think the two are completely different. Science is not benefiting from religion. No discovery of modern science has got anything to do with any religion, no matter what that religion claims. I would say that the most comfortable position to take is that let science go its own way. And if you feel the need for finding purpose in life, not everybody feels that. I mean, there are people who are quite comfortable with having no purpose in life and no higher reference point. They are perfectly moral people. They live lives like everybody else does, perhaps are less harmful to others. They don't go around killing for their beliefs. And so that's a point of view that one could take. I think the best thing, the most important thing is to be good human beings. Thank you, Bruce. Thank you, everybody, for being here. We've had a wonderful discussion. Thank you.
Thank you.